Hello everyone, this is the first class on mechanics of solids. Here we will see the bending of beams and bending moment. So what is a beam? How can we define a beam? A beam is a rod or bar of uniform rectangular or circular cross-section. A beam is a rod or bar of uniform rectangular or circular cross-section whose length is very large, in comparison to its thickness or radius. So beam is a rod or bar of uniform rectangular or circular cross-section whose length is very large in comparison to its thickness or radius is called a beam. In the first figure, a beam of rectangular cross-section is drawn with a length L and thickness T, whereas in the second figure, a rod of circular cross-section is shown with a length L and a radius R. In both cases, we can see that the length is much greater compared to its thickness or radius. Now let us understand the longitudinal filaments in a beam. Consider a rectangular beam. Now this beam is made up of number of thin plane layers and they are arranged parallel to each other. That is a rectangular beam composed of thin plane layers that are parallel to each other and they are arranged on top of each other. And consider one such layer. Consider one such layer like this, and I have drawn it below. And this layer contains number of parallel longitudinal fibers, and we can see that each layer in the rectangular beam consists of number of parallel longitudinal fibers. They are called longitudinal filaments. So the rectangular beam contains the layers which consists of longitudinal filaments. Now let us understand the neutral surface. Now consider a beam which is clamped at one end and loaded at other end. Now what happens to the beam? It will undergo bending on the loaded end. Here the loaded end is the right hand side. Now once the beam bends, what happens to the filaments inside? What happens to the longitudinal filaments inside the beam? When the beam bends, we have a convex side and we have a concave side, and the filaments on the outward side. This side is called the outward side of the beam after it is loaded or after the beam is bent. Now the filaments on the outward side are lengthened and the filaments on the inward sides are compressed. That is, the filaments on the concave side is compressed and the filaments on the convex side is lengthened. This happens when the beam undergoes bending. And we can clearly see that there is a surface in which the filaments are neither elongated or nor shortened. That is, in between the convex surface and concave surface, there is a surface where the filaments are neither elongated or nor shortened. That is represented in the blue shaded region inside the beam, and that surface EFGH, that is called the neutral surface. So what is the neutral surface? Neutral surface is a surface inside the beam where the filaments are neither elongated or nor shortened when the beam undergoes bending. Here EFGH is the neutral surface. Now in which plane the beam undergoes bending? The plane in which the beam bends is called the plane of bending. Here in the figure we have ABCD is the plane in which the beam bends. Therefore, ABCD is called the plane of bending. ABCD is the plane of bending, and we can see that the plane of bending ABCD and the neutral surface EFGH are mutually perpendicular and that intersect inside the beam. So we have a line of intersection between these two planes. That is a line of intersection of the plane of bending ABCD and the neutral surface EFGH. That is called a neutral axis. When the two planes intersect each other, you will get a line. And here the two planes, that is the plane of bending and the neutral surface, intersect inside the beam, and we will have the line of intersection. That is called the neutral axis N dash. Now this is the two-dimensional representation of the beam before bending and after bending. First figure represents the 2D representation of the beam before bending, and I have drawn several longitudinal filaments and N dash, which is the neutral axis. On the right hand side, the figure represents the case when the beam undergoes bending. That is, the beam is loaded on both ends. When the forces are equal and opposite, it will constitute the arc of a circle. Now I have drawn two filaments. One is above the neutral axis and one is below the neutral axis. I have drawn two filaments. One is above the neutral axis and one is below the neutral axis. Now the filaments, what happens to the filaments above the neutral axis? It is elongated, and what happens to the filaments below the neutral axis? It is compressed. So we can say the filaments above the neutral axis will experience a force which points outward, and the filaments below the neutral axis will experience a force that points inwards, and N dash is the neutral axis. When the beam bends, the filaments above the neutral axis will experience a force that is acting outwards, and filaments below the neutral axis will experience a force that is acting inwards. So we have a couple. That is, couple means we have two kinds of forces. And what is the result of that couple? The result of that couple is the torque which is produced at the end. So at each end of the beam, a torque is produced. On the right hand side, the direction of the torque is in the clockwise direction, and on the left hand side of the beam, the direction of the torque is in the anti-clockwise direction. Why the torque is created? The torque is created as a result of the couple which is acting on both the right side and left side of the beam. So what is the result? When the beam is loaded at both ends the torque is created. Since the forces are equal, we have loaded the beam on both side by equal weights. So we can say that the magnitude of the torque is same on both ends, but the direction is different. On the right hand side, the direction of the torque is on the clockwise direction, and on the left hand side, the direction of the torque is on the anti-clockwise direction. And since the beam is loaded equally on both ends, we can see that the magnitude of the torque is same on both ends, but the direction is opposite. Torque is actually the moment of the couple. So we can see on the convex side the filaments are extended and the concave side the filaments are compressed. Now, why the beam bends? The beam bends because of the torque created on both ends. Why the torque is created? The torque is a result of this external couple. When you load the beam on both ends, and due to this external couple on both ends, the beam is bent. The beam is bent by external couple, and the torque is a result of this external couple, and as a result the beam undergoes bending when it is loaded. Now, when the beam is loaded on both ends, it bends. Now, what happens to the beam when it is bent by an external couple? When the beam is bent by an external couple, after some times the equilibrium is reached and the beam will rest in the bent position. So we can say an equilibrium is reached. Why it happens? Because an internal restoring couple is developed at each cross section. Why the beam undergoes an equilibrium state after it is bent? When the beam is bent by an external couple, at the same time an internal restoring couple is developed at each cross section. And after some time an equilibrium is reached, and at equilibrium this restoring couple that is developed at each cross section of the beam, that is equal to the external couple that is trying to bend the beam. So what happens to the beam when it is bent by an external couple? An internal restoring couple is developed at each cross section, and at equilibrium this restoring couple is equal and opposite to the external couple, and the equilibrium is reached. So the beam is bent by an external couple, and at the same time an internal restoring couple is developed at each cross section, and this restoring couple is equal to the external couple at equilibrium, and it is opposite. Now these are the cross sections. I have drawn the cross sections inside the beam. At each cross section the restoring couple is developed. This is one cross section, and this is another cross section. At each cross section the restoring couple is developed, which is equal and opposite to the external couple which is trying to bend the beam. Now let us define the bending moment. What is meant by the bending moment? The magnitude of the restoring couple. The magnitude of the restoring couple is called the bending moment. The magnitude of the restoring couple is called the bending moment. Now at equilibrium we can say that it is equal to the external couple. Since we are speaking about the magnitude, we can see that the magnitude of the restoring couple is equal to the external couple. Now let us find the expression for bending moment. Now consider a cross section of the beam. When the beam is bent under the influence of a external couple, we have a convex side and a concave side, and on the convex side the filaments are extended, and on the concave side the filaments are compressed. And consider the portion CBED inside the beam. You consider a portion, a small portion CBED inside the beam, where CD represents the cross section. Here N dash is the neutral surface, and suppose the beam is loaded, then on the right hand side the direction of the torque is in the clockwise direction. And what is the effect of this clockwise couple? This clockwise couple will bend the beam, so we will call it as the bending couple, and the moment of this couple is the bending moment, and whose magnitude is equal to the external couple. we have seen that at equilibrium there must be an equal and opposite couple to balance the bending couple. Because at equilibrium there should be an equal and opposite couple to balance the bending couple. Now consider the portion CBDE. Now what are the forces acting on the section CBDE? The forces acting on the section CBED are the stretching and compression of the filaments, because the filaments above the neutral surface are in a state of extension and the filaments below the neutral surface are in a state of compression. So the force acting on this section CBED are the stretching and compression of the filaments that is passing through CD. Now consider the equilibrium portion CBED. The clockwise couple will bend the beam, that is called the bending couple. Here CD is the cross section. So there must be an equal and opposite couple to balance the bending couple, because at equilibrium there must be an equal and opposite couple to balance the bending couple. So this restoring couple is equal and opposite to the bending couple. So we can say that if you take a cross section CD, the direction of the torque acting on CD is in the anti-clockwise direction, and the direction of the bending couple acting on the cross section BE is in the clockwise direction. So we have taken a cross section CD where the direction of the torque is in the anti-clockwise direction. So what does this mean? So that type of torque near CD is possible if the forces are acting in such a way as shown in the figure. Because the torque acting at the cross section CD is in the anti-clockwise direction, so we can see the filaments on the upper portion of CD, it is possible if and only if the filaments on the upper portion of CD exerts a pulling force on the right of CD, on the portion to the right of CD. We are speaking about the restoring couple at the cross section CD. The direction of the torque is in the anti-clockwise direction, and that is only possible if the filament on the upper portion of CD should exert a pulling force on the right of CD, that is shown in the arrow on the top portion. Similarly, the filaments on the lower portion of CD exert a pushing force on the right of CD. If this happens, then the direction of the torque on the cross section CD will be in the anti-clockwise direction, and now the direction of this torque is opposite to the torque that is responsible for the bending. Here we are speaking about the cross section CD where the restoring couple is created. Now let us derive the expression for the bending moment. So far we have studied the clockwise couple bends the beam, that is called the bending couple, and we have to find out the moment of this couple. When you find out the moment of this couple, this is called the bending moment. So we have to find out the expression for this bending moment. For that purpose, let us consider the portion CBED again, and on the left side I have drawn the two-dimensional representation of the beam before bending. Now consider a filament PQ which is at a distance Z above the neutral surface N dash. This is the case when the beam before bending. So before bending, the length of PQ and N dash are equal. Now what happens to the same portion when the beam bend? When the beam bend, the length of N dash will not change because it is the neutral axis. Now the length of the filament PQ is extended. This is because PQ is above the neutral axis. Now let us assume that R is the radius of curvature of the neutral axis N dash, and theta is the angle subtended by the N dash at the center of curvature O. R is the radius of curvature of the neutral axis N dash. Now we know that before bending, PQ is equal to N dash because the length of the filament PQ and N dash are same. But after bending, the filament PQ is extended. Why the length of the filament PQ is extended? Because it is above the neutral axis, and when the beam bends, the filament above the neutral axis will extend its length. Now we have angle is equal to arc by radius. Now with respect to N dash, we can say theta is equal to N dash by R. That is N dash is equal to R theta. That is the length of N dash is R theta. Now the filament PQ is at a distance Z from N dash. We can say that with respect to PQ, we can say that theta is equal to PQ divided by R plus Z. PQ divided by R plus Z. Therefore, the length of the filament PQ is R plus Z into theta. R plus Z into theta. Now let us find out how much the filament is extended after bending. How much the filament PQ is extended after bending. Therefore, the extension of the filament PQ is nothing but PQ minus N dash after bending. That is PQ minus N dash. We have PQ is equal to R plus Z into theta, and N dash is equal to R theta. Therefore, the extension of the filament PQ is PQ minus N dash, that is equal to R plus Z into theta minus R theta, that is equal to Z theta. This much the filament is extended. The extension of the filament PQ is Z theta. That is the increasing length of the filament PQ due to bending is Z theta. When the beam is bent, the length of the filament is increased by an amount Z theta. Now let us find out the strain. What is the expression for strain? Strain is nothing but the change in length divided by initial length. Strain is equal to change in length divided by initial length. Now what is the change in length? Change in length is Z theta. Change in length of the filament PQ is Z theta. The initial length is R theta because before bending the length of N dash and PQ are similar. Therefore N dash is equal to PQ is equal to R theta. Therefore strain is the change in length by initial length, that is equal to Z theta by R theta, that is equal to Z by R. We have the initial length PQ is equal to N dash is R theta. And the change in length is Z theta. Therefore, the strain is change in length by original length, that is Z theta by R theta, that is equal to Z by R. Now the Young's modulus of the material of the bar, let us write the equation for the Young's modulus of the material of the bar or beam, that is equal to Y is equal to stress divided by strain. Stress divided by strain will give the Young's modulus. Young's modulus Y is equal to stress by strain. Therefore, stress means the stress causing the strain. Stress is nothing but Young's modulus into strain, because Young's modulus is equal to stress by strain. Therefore, stress is equal to Y into strain. Young's modulus into strain will give stress. Stress is equal to Y into strain. What is strain? Strain is equal to Z by R. Therefore, stress is equal to YZ divided by R. That is, stress is equal to YZ divided by R. Already we have strain is equal to Z divided by R. That is, strain is equal to Z by R and the stress causing this strain is equal to YZ by R. Now let us find out the expression for bending moment. Already we have the expression for the stress and strain, and now let us find out the expression for the bending moment. For this purpose, let us consider an area delta A on the cross section at a distance Z from the neutral surface. Moment means force into distance. Let us consider the force acting on a small elemental area delta A of the cross section. Now this delta A is at a distance Z from the neutral surface. That is represented in the figure on the top left and the top right. You consider a small area delta A on the cross section which is at a distance Z above the neutral axis. That means the filament PQ should pass through this area's delta A. So we are going to find out the expression for bending moment. For this, let us consider a small area delta A in the cross section which is at a distance Z above the neutral axis NN dash. We have the filament PQ is also at a distance Z above the neutral axis. So we can say the filament PQ will pass through this area delta A. We have derived the expression for stress, that is equal to YZ by R. Now what is stress actually? Stress is the force per area. Now force acting on this small area delta A, we have taken a small area delta A on the cross section. Now what is the force acting on this area due to bending? What is the force? When the beam bends, there is some force that is acting on this small area delta A on the cross section. Now what is the force acting on that area? That is equal to stress into delta A. Already we have determined the stress as YZ by R. Therefore, the force acting on that small area delta A when the beam undergoes bending is YZ by R into delta A. Now let us find out the moment of the force. Moment of the force means force into distance. Here the distance is taken from the neutral axis. So it is actually the moment of the force about the neutral surface. The moment of the force about the neutral surface, that is equal to force into perpendicular distance. We have the force acting on the area delta A is yz by r into delta A. Now what is the moment of the force about the neutral surface? It is the force into perpendicular distance from the neutral surface, that is equal to yz by r into delta A, and this delta A is at a distance z above the neutral surface. So we can say that the moment of the force about the neutral surface is yz by r into delta A into perpendicular distance, that is z. So this is y z square by r into delta A. This is the moment of the force about the neutral surface that is acting on the small area delta A. This is the moment of the force that is acting on the small area delta A. Now what is the total moment of the force acting over the whole cross section? That whole cross section contains several such small areas. Therefore, the sum of the moment acting over the whole cross section is sum over y by r delta A z square, that is y by r into sum over delta A z square. This is because y and r are constant. This sum of the moment of the force acting over the whole cross section is called a bending moment. So what is bending moment? Bending moment is the sum of the moment of the force acting over the whole cross section. Now in the expression of the bending moment, we have y by r into sum over delta A z square. This sum over delta A z square is similar to the moment of inertia we have already studied. What is moment of inertia? It is sum over dm r square. Here we have a term sum over delta A z square. So this term is similar to the moment of inertia we have studied. Therefore it is called the geometrical moment of inertia. It is a geometrical moment of inertia of the cross section about neutral surface. So how do you find the bending moment? Find the moment of the force acting on a small area. Take the sum of the moment of the force acting over the entire cross section. So you have the equation y by r sum over delta A z square. This is the expression for bending moment. Now here the sum over delta A z square is the geometric moment of inertia of the cross section about the neutral surface, and we are representing it as Ig. Therefore the bending moment m, that is equal to sum over y by r delta A z square. Y and r are constant, so you can take it outside. So m is y by r sum over delta A z square, that is y by r into Ig. This is the expression for the bending moment. So what is bending moment? It is y by r Ig, where Ig is the geometrical moment of inertia. We can write Ig is equal to ak square, where A is the area of cross section. Moment of inertia is mk square. In the same way, you can write the geometric moment of inertia as ak square, where A is the area of cross section of the beam. K is nothing but the radius of gyration. Radius of gyration. K is the radius of gyration of the cross section about the neutral surface. The bending moment m is y by r Ig. Ig is the geometric moment of inertia, that is equal to ak square. Now let us consider the special case of geometric moment of inertia Ig. Consider a rod of rectangular cross section. Let B is the breadth of the beam and D is the depth of the beam. B is the breadth of the beam and D is the depth of the beam. What is the geometric moment of inertia Ig? Ig is equal to ak square, where A is the area of cross section. If B is the breadth of the beam and D is the depth of the beam, we can say the area of cross section is BD. Now, please remember that for a rod of rectangular cross section, K square is equal to D square by 12. Therefore, Ig is equal to AK square, that is BD into D square by 12, that is Ig is equal to BD cube by 12. That is, for a rod of rectangular cross section, the geometric moment of inertia Ig is BD cube by 12. Therefore, what is the bending moment? Bending moment M is equal to Y by R into Ig. Bending moment M is Y by R into Ig. That is Y by R BD cube by 12. That is the bending moment M, that is equal to Y by R BD cube by 12. M is equal to Y BD cube by 12R. Now consider another case for a rod of circular cross section. We know that A is equal to pi r square, and remember that for a rod of circular cross section K square is equal to R square by 4. Therefore Ig is equal to pi r raised to 4 by 4. Here again the bending moment M is equal to Y by R into Ig. M is equal to Y by R into Ig, that is equal to Y by R pi r raised to 4 by 4. M is equal to Y pi r raised to 4 divided by 4 into R. These are the special cases of geometric moment of inertia and bending moment for a rectangular and circular cross section. Now let us define the term flexural rigidity. We have the bending moment M is equal to Yig divided by R. Now consider the case when R is equal to unity. When the radius of curvature is unity, the bending moment is equal to Yig. Now this bending moment is called the flexural rigidity. That is, bending moment is equal to flexural rigidity when the radius of curvature is unity. Bending moment is equal to flexural rigidity when the radius of curvature is unity. Now let us define the flexural rigidity in the following way. Flexural rigidity is defined as the external bending moment. Flexural rigidity is defined as the external bending moment required to produce a unit radius of curvature. Flexural rigidity is defined as the external bending moment required to produce a unit radius of curvature, and the equation is Yig. What is the significance of this flexural rigidity? What is the significance of flexural rigidity? Flexural rigidity is a measure of the resistance of the beam to bending. How much the beam is resistant to bending. The measure is actually the flexural rigidity. It measures the resistance of the beam to bending.